We are recording.
Okay.
We can start.
Okay, it's a pleasure for me. Good afternoon, everybody. Pleasure for me to introduce Benedetta Vulcani, who is a colleague but also a friend. Okay, we started a PhD in Padova, only 1 year difference. From there she started to work about galaxy formation, evolution, especially in the morphology, focus on the morphology of galaxy, and also the substructure inside the galaxy and the relationship between them and the fire. Since then, she moves around the world in several places. I will mention just a few, like Tokyo, Melbourne, and also Qatar. She is today the INAF representative of MICADO, which is the first light instrumentation for the ELT. And today she will talk about scientific results, also focusing on the progress that MICADO gave us with this new instrumentation. Thank you.
Thank you. So, good afternoon, everybody. It's really a pleasure to be here. This is my first time here in Teramo, so I'm really excited to meet you all and see the place. So, as Elisa said, the talk tomorrow will mainly focus on galaxy morphology, and I will discuss why studying morphology is important, what we can get by studying the morphology of galaxies, and the main results about the different morphological function and how the incidence of the different morphological types evolve with time and how they depend on other properties, internal properties such as stellar mass, and external properties such as the environment in which galaxies are found. And then I will show you how we currently live in a phase where we cannot make too much progress with current instrumentation, so we really need to expect MICADO to see the universe at high redshift with new eyes to really distinguish about the different formation channels for galaxies. So, just to start very basic, we know the galaxies appears in many different shapes and sizes. It's very immediate from these galaxies in the local universe that a variety of morphology exists. And it's important to stress that morphology, even though it's apparently an easy way to classify galaxies, it's not important just as a mere classification scheme, but it can really give insight on how the galaxies formed and why they came to be. Indeed, in general, we can characterize the galaxy population as binary. On one side, we have these galaxies that are the elliptical galaxies, and also these are the zero, as I will talk to you later on, and that are the early type galaxies that you see have a very smooth light distribution. They are quite spherical, as zero also have a disk. But in general, these galaxies are typically old. They don't have very high levels of star formation. They are red. They do not host, they do not have a lot of dust. On the other hand, we have the spiral galaxies and irregular galaxies that, on the contrary, are very blue, meaning that they are forming stars at a very high level. They are gas-rich, and especially spiral galaxies are very well structured. You see all these spiral arms that are dominated by rotation. So, by studying the galaxies morphology, we can infer the environmental history, the evolutionary history, we can understand how the different components ascend over time. This is an example. In the local universe, we will see later on what happens when we move to higher redshift. As I said, morphology seems a very easy way to classify galaxies. And indeed, this historically has been really one of the first ways that has been used to classify galaxies. And we can even date back to 100 years ago when Hubble proposed the tuning fork. So we have on the left the elliptical galaxies, and then on the right there are the spiral galaxies that, depending on whether they have a bar in the center or not, they can be subdivided into barred and unbarred spirals. And the lenticulars are kind of in between because they share some properties with the ellipticals. They have a very well-defined badge, the stellar population is old, but they still have the presence of a disk, similar to the spiral galaxies. Initially, it was thought that this was an evolutionary sequence. Galaxies start from being spirals. As the population ages, we moved towards a more elliptical morphology. But now we know that this is not very true. Even though galaxies transform, and I will show you later on, this is more tricky than it can appear, because the tuning fork changes over time. Here we have a representation of a tuning fork today and a higher redshift. So the progenitors of elliptical galaxies cannot be found in galaxies that have spiral morphology today, but their progenitors are galaxies that were kind of start forming in spiral late-type galaxies many, many years ago. And you can appreciate, even though this is very small, that the morphology really changes across time. As we go back in time, and especially the cosmic noon around redshift 2, galaxies were characterized by much more clumpy structure. The medium was much turbulent, so the condition that galaxies were found in were very different. And so, as a consequence, the progenitors of the local spiral today were very different than spiral galaxies today. And so this is something that it's important to keep in mind in general when people try to connect progenitors and descendants and understand the evolution of the morphologies. But how can we can measure the morphology? There are many different ways. As I started, the easiest way is, and the first way the galaxies have been classified, is by using a visual classification. So going through the image and really inspecting the galaxies and assigning them a class. And this approach is very powerful because the human eye can really capture some structures and some features that are very hard to be picked by any automatic algorithm. On the other hand, however, this is very time-consuming. It also depends on the experience of the classifier. It depends on the quality of the data. And it's really not sustainable for the big data sets that we have nowadays. So obviously, people over the time have tried to find new ways. The next method that is largely adopted is using some parametric light profile fit. So we apply some analytic model, we assume some analytic models, and we apply a fit to the light profile. And in this way, we can characterize, for example, the radius in which half of the light is included. We can measure the Cersei index that tells us, let's say, how much bulgy the galaxy is. And then we can measure, for example, the bulge to focal direction. However, the problem of this is that we assume that there is a smooth idealized profile. But as we have seen in the examples before, galaxies can be clumpy, very irregular, asymmetric. So this relies on some assumption that might not be true. So next, people have started using non-parametric morphological classifications. And this really quantifies the light distribution without having an underlying assumption on the model. And these methods are really sensitive to asymmetries and disturbances. The most common metrics are the concentration, asymmetry, and smoothness proposed by Concelis back in 2003. And then there are also the Gini and M20 parameters that really characterize the light distribution and the clumpiness. And then there is a combination of these parameters that actually can trace back to the visual classification, so we can still subdivide galaxies in elliptical, lenticular, spiral, irregular, and so on. Then, just for completeness, we can also use some tools that characterize the shape of the isotopes, so how the light is distributed at different distances from the galaxy center. So by studying the shape of the isotopes, we can really identify bars, interaction, warps, and so this is another way to characterize the morphology from the photometric point of view. And then the last method is actually that instead of using the photometry, we can also use the kinematics. So by studying the velocity of the different components in the galaxies, for example, of the stellar components and the gas components, it's possible to identify the different sections of the galaxies. So separate disks and spheroids that are expected to move within, to have a different rotation. Clearly, nowadays, all of these methods can be followed up with machine learning techniques and any automatic classification that help us to, especially to classify galaxies in this area of big data, where we really are facing with a huge amount of data. So the visual classification, as I said, works very well in the local universe. Here, almost everybody is able to distinguish between an elliptical and a spiral galaxies. But what happened when we move to higher redshift? This is quite an old paper, but it really captured this is one of the first times that it was really shown how the morphology changes with time. And as we move from redshift 0.75 here up to redshift 3, you can really see that the morphology changes. Galaxies become much more clumpy, and a spiral structure doesn't exist anymore. So as you move to higher redshifts, getting a robust and reliable morphological classification is harder and harder. So at some points, it's not useful anymore to call a galaxy a spiral galaxy or not. One thing you can do is really to quantify the importance, for example, of the main clump, count the number of clumps, so on and so forth. But in general, people have tried to, anyway, identify groups of galaxies, and so classified and quantified how the different morphological fractions vary as a function of time. In this plot, it's small, but hope to see, we have the fraction of galaxies of the different morphological types as a function of redshift in 3 different stellar mass bands. If you look at the rightmost panel, we have the most massive galaxies. And here, from redshift 0 to redshift 1, all trends are rather flat. And especially, the population is dominated by these 2 reds of colors that are ellipticals and bulge-dominated galaxies. So, among the most massive population, already at redshift 1, the vast majority of galaxies is already elliptical and bulge-dominated. This population was already there at redshift 1. Most massive galaxies already reached the final stage of the revolution, and so they are already bulge-dominated or ellipticals. If instead we focus on the leftmost panel, which is the lowest mass spin, we see a dramatically different situation. Here at all redshift, the population is dominated by spiral galaxies. And now also we see that we have a decrease in the fraction of spiral galaxies from redshift 1 to redshift 0. So we have a hint that from redshift 1 to redshift 0, galaxies are transforming. And what are these spiral galaxies becoming? This decline is mirrored by the increase of bulge-dominated galaxies. So we have a first hint that the spiral galaxies are getting lost. And so you have an increase of the bulge-dominated galaxies. And this has been shown, obviously, in many, many works. But what happens when we move to even higher redshift? This is another plot that shows, again, the morphological fraction of disks in blue and spheroidal in red, just forget the irregulars. And here we have 3 beams in redshift as a function of stellar mass. And when we move to the higher redshift beam, that is here above redshift 2, we see a different situation in the sense that at the highest masses, we do not have this huge predominance of elliptical galaxies. So this means
The stellar mass is from the
in this case, I think it's SED fitting putting together, yeah, from the luminosity, but not just from one band, from the multi-band photometry. We see that here the fraction of disk and spheroidal is very similar. So we are capturing between redshift 1 and 2 an epoch where even massive galaxies are transforming. So this is really the phase where a lot of transformation are happening. So redshift 2 starts being really an epoch where we need to characterize in details to really understand the mass assembly. This seems more or less quite neat and clear, but we need to consider another parameters. Galaxies are not randomly distributed in the universe, but they really live in different environments. This is a snapshot of a simulation of dark matter that really shows the distribution of dark matter in the universe. And you can see that there are many bright nodes, and these are the nodes of this big cosmic web, and these nodes are connected by these long bridges that are the galaxies. And depending on where the galaxies live in this cosmic web, their life can be dramatically different. So we can have galaxies that are in the field, they are isolated, far from all this action that happens in these dense regions of the universe. And in most of the cases, their life is really dominated by internal mechanisms. So by the stellar mass, by the presence of AGNs, for example, so some feedback, but they don't have any external stress that affects their evolution. Then we can have galaxies that live in these long bridges that are filaments. Filaments are considered as the highways that leads the material, leads the galaxies from some low density regions towards the cosmic web. And in this case, this is the first time galaxies start feeling a higher density medium. The gas could be hotter. And so this is really the first phase where galaxies can feel environmental effects. The filament field is quite a new field. There are still a lot of works on filaments, and results are still not defined. So in what I will follow, I will very rarely talk about filaments because the results are still, there are many results that are still discordant. Then galaxies in these bright knots can be either in a group that is an association of few tens of objects, or even in galaxy clusters. Clusters are really the densest and hottest regions in the universe. They are the most massive systems that we know of. They are radialized, and they are really permeated by a dense medium and gas that really affect the distribution of the gas in the galaxies. So these are really the sites where environmental effects is the strongest, and we can expect the galaxies to be the most different with respect to galaxies of similar mass in the field. However, it's not as easy as it is here, because even the environment changes with time. Here we have again a simulation similar to one that I showed you before, but we have 3 different snapshots at 3 different epochs, from redshift 4 to redshift 0. And you can really see that even though already at high redshift you can see this structure, this cosmic web, the structure really formed later on. We have the material that condenses along these cosmic filaments, and so the density contrast is much higher in the local universe. So the effect of the environment changes, and the definition of the environments can change from high to low redshift. This is from the simulation, but also if we just look at 2 clusters in the observation, we can appreciate the difference. This is the Perseus clusters. This is a Euclid image, and you can quite easily see all these galaxies that share a similar size and similar colors that really stands out from the background. These are all galaxies that belong to the same structure. But instead, if we move to higher redshift and we look at an image that is the spiderweb protoclusters, and this is a cluster that is very well studied at redshift 2.16, here you see that all the circles are the member of this system, but it's very hard to distinguish them from the background. We really need advanced methods to establish whether the galaxies do belong to the system. So when we want to compare high redshift clusters of the progenitors of the nowadays clusters that are called protoclusters and current clusters, we really need to be careful that we are not introducing biases, because the systems are very different. So as for morphology, also for the environment, we can use many different definitions of environment. And it's very important to know which definition is used, because they can really trace different aspects. Here, I will just show some sketch of different methods that can be used for determining the environment. So, for example, we can use group finders that are friend-of-friend algorithms that are work very well at the group scales and really connects galaxies that share similar velocities and are in the same physical space, and so we can identify the groups. Then we can use some method to measure the so-called local density. That means we count how many galaxies there are around each of the galaxies of interest, and we can do this by counting the number of galaxies by determining the area within which a number of galaxies, in this example 3, it could be 5, 10, can be found with respect to the main galaxy, or we can fix an aperture and count how many galaxies there are within this aperture. Then we can do some clusterings, some other more complicated methods, or especially for the cluster, for characterizing clusters, we need to have information on the dark matter distribution, characterize the gravitational potential, and so identify these regions that have the deepest potential wells. And so this is very powerful for determining the main galaxy in the cluster, that is the brightest cluster galaxy, that it's really sitting at the bottom of this potential well. And then there are some techniques to associate the galaxies that are part of the same dark matter structure in the cluster. In general, each of these definitions carry different information because they really probe different physical scales. So when we look at local density, for example, we look more at galaxy-galaxy interaction, things that happen around the galaxy. When instead we look at the gravitational potential at the cluster scales, we are more sensitive to the processes of the dense gas that permeates this medium affect the galaxy's life. So as I said, galaxy clusters are really the most massive systems in the universe. They are relaxed. And in the local universe, most of the galaxies are elliptical, are also red and passive. And this is very different from what we see in the field. So this is the first indication that clusters are able to affect the morphology of the galaxies. But as I showed you before, the local clusters look very different from the high redshift clusters. And this is because clusters are open boxes. There is a continuous inflow of galaxies from the field toward into the clusters that give new life, let's say, to cluster, but gives also a lot of material, new galaxies that are late type and start forming, and as they enter the cluster, they become elliptical. It's important to keep in mind that galaxies can fall into the clusters at different cosmic epochs. They can also fall as isolated systems. Galaxies can fall first in a group and then falling into the cluster as a group. They can fall very early on, they can fall later on. So even clusters host a very heterogeneity of situations. So it's very hard to find a unique path. But in general, before we looked at the morphological fraction as a function of redshift and stellar mass, we can now add the environmental piece. So here we have again the morphological fraction as a function of stellar mass in the local universe in clusters. And what we see is, as we saw before, the most massive galaxies are most likely elliptical. But in clusters, this is even more evident with respect to the field. 100% of the massive galaxies are elliptical. So this is really an indication that clusters really transform these objects. The fraction of spiral galaxies decreases with stellar mass, and it's anyway very low. It's less than 20%. And in local clusters, at intermediate masses, we have the predominance of these lenticular S0 galaxies. This is for the cluster. We can do the same in different other environments. So here we have the isolated systems that are galaxies that do not have any neighbors around them. Then we have the pairs that are just a couple of galaxies that are isolated from the rest of the universe. Groups that are, to some extent, small-scale clusters. And then we can have also the field that is just the sum of the others. What we see, if we see the groups, we see that even though also in groups, massive galaxies are most likely elliptical, at lower masses, we do not have this predominance of S0. So S0 galaxies are really a cluster-specific population, let's say, or they are anyway more important in clusters. But the important thing is when we look at the isolated system, which really have a completely different behaviors. We see that at all masses, spiral galaxies dominate the isolated population. So we really have the confirmation that if galaxies are not affected by the environment in the local universe, they are normal late type spiral galaxies. So again, it's a proof that the environment affects significantly the morphological distribution. Here I'm talking just about morphology, but we can recover similar trends also when we look at galaxy color or star formation, really indicating that all these quantities are interrelated. As I said before, we can define many different environments. So what we can do, and what's been done quite largely, is studying the local density within the clusters. And here on the left, there is a morphology density relation in cluster. This is really one of the first extragalactic studies that has been done in the 80s by Dressler. And it really showed that the fraction of elliptical galaxies increases with increasing local density, and the fraction of the spiral galaxies decreases. In this work a couple of years ago, we really extended the sample, and we reached the external region of the clusters, really to take into account this transition region that is dominated by these new galaxies just infell into the clusters. And here on the right, we have the same morphological fraction, but as a function of cluster-centric distance. So depending on how far from the cluster center the galaxy is. And what we see is that the fraction of spiral galaxies increases from the galaxy center to the external part. And in the external part, it really reaches this horizontal line that is the reference field value. So in the cluster outskirts, the situation is very similar to what we have in the field. But interesting, for the elliptical galaxies, we see an important and peculiar trend in the sense that the fraction of elliptical galaxies is very constant with the cluster-centric distance, except in the cluster core. And keep this in mind because I will explain why this happens and how we can interpret this in 2 slides. As I said before, we can use different morphological parameterization. And Capellari in 2011 used the kinematics information, and so it studied the morphology kinematics local density relation. And it found that galaxies can be subdivided into slow rotators, that are the elliptical galaxies that have very little rotation, and fast rotators, that are the S0 galaxies, and then there are the spiral galaxies. So it tried to understand whether the origin of this morphology density relation can also be related to how fast the different components, it can be related to the angular momentum of the galaxies. And what it found is while spiral galaxies always decreases, for the slow rotators here, we have that they are almost absent at very low densities, and they have only a dip in at the very highest densities. And this will correspond to the cluster cores that we've just seen in the previous slide. And then we have these fast rotators that more or less correspond to the S0 galaxies that also have an increase with local density. So if we try to put together the results from the pure morphology and from the kinematics, we can try to explain why elliptical S0 and spiral galaxies is different origins. So I just go to the results because otherwise it's too long. The idea is that elliptical galaxies are mostly slow rotators. The dependence on local density is much stronger than the dependence on the distance. So these elliptical galaxies are really the primordial population in cluster. It's a population that has been in cluster since very high redshift, and they really form in the nodes that we have seen in the plots before of the cosmic web, where the densities were already high at very high redshift. These density peaks corresponds to the center of the galaxy clusters. So this primordial population is the backbone of the cluster population that has been there forever. So the high density regions correspond to the center of the galaxies. And at the end, in the later phases, the cluster-centric distance does not matter anymore because it's simply a byproduct of the fact that the densest regions of the universe are also in the cluster core. Instead, for the S0 galaxies and late-type galaxies, the situation is different. Here we have the local density on the x-axis in 3 different cluster-centric distance spins. This can be considered the cluster core, and this is the cluster outskirts. And here we have the fraction of S0 and the relative fraction of S0 and spirals. And what we see is that on this side, the trends are most likely flat. So here, it's more important, the cluster-centric distance. And only in the outskirts, we see some trends, even with the local density. So this means that the transformation between S0 and spiral galaxies is really induced by the cluster-centric distance. So as the galaxy from the field enters into the clusters, it feels the cluster effect, and so it loses its spiral arms, and this is because the gas that is the medium, the gas that is within the clusters affect the galaxies, for example, through RAM pressure stripping. It removes the spiral arms, and we are left with a S0 galaxy, which is a disk galaxy with no spiral arms. This transformation, to confirm this transformation, obviously, it's possible to go to higher redshift. And so here we see the same results in a higher redshift beam between 0.5 and 1. And here we have the fraction of elliptical galaxies, of S0 galaxies, and of spiral galaxies plus irregular as a function of time or redshift. And we see that the fraction of elliptical galaxies is very flat up to redshift 1. So the elliptical population in clusters was already there at redshift 1. Well, we really see that these trends are mirrored because we have this transformation of spiral galaxies into S0. We can also see similar trends as a function of cluster-centric distance, where the fraction of spiral galaxies increases from the center toward the outskirts. The fraction of elliptical galaxies is rather flat, except for the first point, and the fraction of S0 galaxies is, you can see in this plot, the signal is not very strong, but it's also here quite flat. And finally, we can also look at the dependence on stellar mass. This is a plot we have seen before with the addition of the redshift 0.6. And we see again that the trends for elliptical galaxies is very similar at the low and high redshift. But the fraction of late-type galaxies and S0 galaxies is really flipped between these two redshift bays. So it's really clear that in this cosmic epoch, within these two epochs, we have this transformation that is taking place. So it's really clear that between redshift 1 and 0, we have a transition. But the real challenge actually starts at cosmic noon, because we know that the cosmic noon is an epoch where we had a lot of star formation, the medium was very turbulent, so we expect that a lot of activity happens at high redshift. But we have many issues. At high redshift, morphology is harder to measure, environment is harder to define, but still, we start seeing some trends. At redshift 2, the galaxies are most likely late type, they are clumpy, they are very irregular. But there are some works that have started still seeing some morphology density relation. Here we have the early type fraction as a function of local density in clusters at redshift 2. And we see some hints that there is still a dependence on local density. But these are just a few clusters, and in general, the trends are still very debated. When we consider only the star-forming galaxies and we see the fraction of disks in different cluster and protocluster at redshift 2, we do not see any dependence on galaxy density. So at redshift 2, as long as the galaxy is star-forming, the fraction of these galaxies is completely independent on local density. So as long as it forms stars, the morphology is not changing. So overall, this situation goes in the same direction that we see morphology density in place already at high redshift, but we need always to be careful about which is the sample that's being characterized. And in general, there are many other results that actually do not find any trend. So the situation is still very complicated. So as I said, morphology is much harder to get at high redshift. This is, again, the same example. But we have, as I said, we have an increase of the clumpy galaxies. And indeed, here we have the fraction of clumpy galaxies as a function of redshift. And all of these different studies really show that there is a steep increase in the fraction of clumpy galaxies with respect to the fraction of not clumpy galaxies as we go to to high redshift, to the cosmic noon. But why are these clumps very important? What are these clumps? What do we know until now? So we know that these clumps are typically observed between redshift 1 and 4. And with the current instrumentation, they are typically only marginally resolved. We expect that they should have sizes between tens of parsecs to few kiloparsecs, but the smallest clumps are really out of reach with current instrumentation. All these galaxies that host these clumps typically have high gas mass fraction, they have high velocity dispersion, and there are many indications that show that these clumps are really formed in situ within these galaxies. And given the high velocities and high gas fraction, they can really survive the physics. But we really want to understand more about how these clumps are formed, so we really need to get better data. So to make progress, we need to resolve clump at sub-kiloparsec scales. We need to be able to have a better environmental separation, and we need to be able to measure both the morphology and the physics that is happening at the same time. And for this, we really need to wait for MICADO. So this, before going into the detail of MICADO and DLT, this is just a slide to capture your eyes. So here we have a model of 3 small clumps. And here, with this simulation that is done by a postdoc in Padova, Matteo Simeoni, we can see how JWST sees this clamp and how MICADO will see it. Obviously, this is just one representation, but what MICADO just detects as one structure, with MICADO, we could really start distinguishing among the different subclamps. So we will come back on this later, but ELT is the world's largest optical near-infrared telescope that is obviously, as you all know, constructed by ESO. It will be 30 meters, it will have 30 meters primary mirror that will be composed of about 800 hexagonal segments. It really performs at the best capabilities with AO-assisted observation to really reach the highest possible angular resolution, and it will have wavelength coverage between the optical and the near-infrared. The first line instrument is MICADO, that will provide imaging, astronometry, slit spectroscopy, and coronagraphy. At the first stage, MICADO will be built on the NASMIC 8, and it will be equipped by SCAO adaptive optics. But then, when Morpheo will come along, MICADO will be moved to the NASMIC B. Just in a nutshell, MICADO will cover the wavelength range between 0.8 and 2.4 microns. It will have a field of view of about 51 times 51 arc seconds, and it will have a 4 mass pixel scale. There will be also a setup with 18 by 18 arc second with even much higher physical scale. It will have a number of different broad and medium band filters, and it will also be equipped with a slit that will have a length of 3 arc seconds and a width of 16 mass. As a timeline, we are really in the phase of manufacturing. We are proceeding quite well, and we expect that the first slide will happen between 2029 and 2030, depending on what you define as first slide, if the instrument, science, whatever. But let's hope to stick with the 2030. Just to put the spatial resolution in context, here we have the expected resolution of MICADO in the center compared to what we can have, for example, with HST at 2 microns, with JWST or VLT at 2.2 micron, with ALMA, and you really see how better ELT will perform with respect to the other instrumentation. Just to have an example, we expect to be able to have a resolution of 0.4 milliparsec at the galactic center, but really to have 80 parsec at cosmic null. And this will be really the sweet spot to characterize the clamps, because we really need to go to this order of magnitude of size to really characterize the physics in the clamps. So, as I said, we will have 2 different models. At first, we will have the SCAO, so we will have a magnitude range of the reference stars that will have to be between 7 and 16 magnitude in R. The AO will be able to work on extended objects, at least up to 1 arc second diameter, and the correction will provide a good field of view up to 20, will provide good performances up to 25 arc second off axis from the guide star. The situation will clearly improve when Morpheo will come along, because the MSAO performances will be much better. We will require to have up from 1 to 3 natural guide stars. They will be complemented by 6 laser guide stars. We'll have a much larger coverage, so we'll finally be able to select the targets based on our scientific interest, and not only because we have a star there, and so we need to observe that piece of sky. Obviously, to have a good performances, we need to have a very well-detailed knowledge of the PSF. So why do we need the PSF? Because we really need to be able to get precise fluxes and position. We need to be able to detect and measure all the structural parameters that we are interested in for our extragalactic cases. And we need to be able to remove the point-like sources that could affect our observation. So, for example, foreground stars, exoplanets, QSO, and so on. So, how will the MICADO Consortium, how is the MICADO Consortium organizing themselves? We are adopting a pure PSF reconstruction method. That means that this method is done without the use of science data. So we will obtain a blind derivation in post-processing of the PSF of a given observation. We will not use any science data, but we just use the telemetry. And the goal is to really be able to obtain a PSF reconstructed both on and off axis. This method is typically insensitive to the waveform sensor type, and we are now in the phase of testing the routines and we are more focusing on the SCAO performances. We will move to the MCIO in a later phase. Results are promising, and I will show you some now. So, but the question now is, why do we actually need to have this pure PSF reconstruction? The problem is that we do not have enough reference stars in the fields we are interested in. In all extragalactic cases, in most of the extragalactic cases, or in at least in 40% of the targets, we do not have suitable stars for which we could perform a standard PSF characterization. With some simple calculation, we found that in the good field south, we can expect only 1 star more or less per square arc minute. So we really need to find a solution to solve the issue. And this is by default, let's say, because for the extractive science, people have always focused on fields that do not have stars to have a better observations. So in Padova, together with Elisa and other people in Rome, we are part of the PSF reconstruction working package. And so the goal is to provide a PSF reconstruction service that will be delivered first to the MICADO consortium, and then it will be something that each user will be able to use. So the idea is really to reconstruct the PSF of MICADO, both for SCAO and for MCIO, using only the AO and non-AO telemetry data. And this will be a process that will happen in post-processing. So the user will have to do this after the observation will be taken. The concept is an old concept from Varang et al. 1997, but we are performing a lot of tests and developments. So this is just the entire consortium that, in addition to Padova, to INAF, includes many other partners. So in Padova, we are more, with Elisa, we are more focused on characterizing the performances. We are not focused in directly developing the tools, but with some data, we are testing the performances. So here, there is an example of one of the first tests that we ran, and so we use some Sol-Lucy data to reconstruct the PSF. Here on the left, you have the observed PSF. On the right, there is the reconstructed, and here you have the normalized difference between the two. And here you can see the PSF as observed and reconstructed as a function of distance. And you can see that in this case, when we simulated the SCAO on axis, we have a quite good results. The stress ratio is the difference is between about 1.7. The full width at Maximus is the relative difference is 4.4. Then circular energy is 4%, and the size is almost 4%. So what does this translate into our scientific interest, into our analysis? So what we did with this PSF, we simulated with Galfit a galaxy, a redshift about 2, with known parameters. And then we tried to measure the input parameters to see the difference between a good knowledge of the PSF and a no knowledge of the PSF. So here on the first column, you have the control PSF, meaning that we used the same PSF to create the galaxy and then to remeasure the parameters after the simulation. Then in the second column, we have the reconstruct PSF that we did. Then we have the comparison with the diffraction limited PSF and with no knowledge of the PSF. And you can really see that even with just first attempts, let's say, of reconstruction of PSF, we can reach very good agreement between the control case and the reconstructed. There is still some issues, for example, with the Celsius index, but still we recover the same morphology of the object. In contrast, having no information on the PSF really gives some dramatically wrong results. We are now making some progresses, and here we are analyzing some ARIS data. This refers to some commissioning data, but now we are also adding some TTR observations. So again, you have just a comparison of the observed and reconstructed PSF and the relative difference. And in this case, we are exploring even some cases of axis. We are playing with different filters, different turbulent conditions to really test the different possibilities. And overall, again, results are very promising. At the same time, we are also, again, trying to figure out what all of this can mean for our observation and our interest in characterizing the morphology and clumps in galaxies. So here in this test, in this simulation, we have simulated a galaxy at redshift 2 with just one clump. And then we run a simulation and we obtain the output of the simulation where only the clump actually is visible. And then we measure again the parameters after the simulation, knowing the PSF, and so the difference between the input and the output obviously gives us an indication on how good we did to perform the reconstruction of the PSF. So overall, if we perform the simulation using a MICADO SCAO configuration using a PSF for a case 30 arcsecond off axis, we get about 20% error in the recovering the measure of the effective radius and 0.1, 0.2 magnitudes in recovering the error on the magnitudes. So what does all of this mean actually again for science? So here we have a plot that shows for hypothetical clumps their magnitudes and the effective radius. And so and here we draw with you two lines that really show which are the clumps in this space that will be possible to measure with MICADO. We simulate two cases, one with strain ratio of 12%, which is the typical strain ratio that we could have in the SCAO configuration, because the typical strain ratio we can have at the edges of the field of view if the star is at the center. And then we have a more promising case where the strain ratio is more or less 60% that correspond to optimal condition in Q1 for the simulation. So overall, for the strain ratio 12%, we will be able to observe the population that stays here. For the better condition, we will go down to absolute magnitudes of about minus 15. But what does minus 16? Sorry. But what does this mean? So let's try to populate this graph with observations that are currently available. So first of all, we need to remember that given the pixel scale, all of this would not be accessible even by MICADO, but they will be accessible only when we use the lensing that really magnifies the sizes and the luminosity, and so we could access this area. And all the points that are currently available are really here. These are all JWST observations from different works, and they are all based on lensing. And you can really see that this population here is the one that is more magnified. So to really reach these very faint objects, we really need to use high magnification. But overall, MICADO will be, let's say, comparable to what JWST is doing with lensing. Again, just to try to understand this a little bit more, we go back to an example of the simulated case. Here we have one clamp that actually is made of 3 small clamps. If we measure the magnitude and the size of this system goes here in this plot. If we observe this galaxy, this clamp with JWST, this is what we would get. So we could characterize the global properties of this clamp, but we could not characterize the internal structure. Instead, if we use with some simulation of MICADO, we will have that in the case at least of the 60% strain ratio, we will be able to distinguish the 3 clamps that will be, in this case, placed here. So there will be a very high increase in our knowledge of this population. But as final thing, this is again without lensing, but we know that we can use lensing. And if we put together lensing and MICADO, this will really be the deepest view that we can have. And to try to investigate this further, we are trying to characterize lens galaxies in Abel 2744. So this is one of the best studied clusters in from JWST, and in general, it has a high magnification power. And we are trying here to unify the interest in morphology with the interest of the environment, because we are looking for protoclusters that are magnified behind these clusters. So we identify 4 possible structures that are protoclusters, and with the postdocs in Padova, we are characterizing the morphology of these galaxies that are lensed and we know are in dense environment. This work is ongoing, so I don't have results, but the main idea is to try to characterize with JWST images this population and then simulate what we could actually see for these clumps for MICADO, really to understand if these that look like just one clump, one galaxy, actually are made of many different substructures, and try to understand more their assembly. So next time I will show you this result. So I conclude here, and just to summarize, I hope I've convinced you that morphology is really a fascinating and important tool, vehicle of information to understand how galaxies assemble. Morphology really depends on stellar mass, on redshift, and on environment. Overall, in the local universe, the morphology density relation, morphology environment relation are quite well established. We can see how spirals transform over time and in different environments into S0, and so they really can give us information on the role of the environment and all the processes that affect the galaxy in dense environment, while elliptical galaxies are still the population that is called primordial population because it's been in these dense regions in clusters, let's say, forever. At cosmic noon, the situation changes. The galaxies are more clumpy, turbulent, are more star-forming, and there are some work that really show that morphology density is already present at redshift 2. But actually, we still don't know if this is true, and we don't have information at even higher redshift. But as we go to higher redshift, both morphology and environment are harder to define. So one way forward is to really focus on clumps that are really the key building blocks of galaxies. And to try to understand their formation, we really need to have better facilities to really resolve them. So we need sub-kiloparsec scale spatial resolution, and obviously an accurate knowledge of the PSF. So MICADO will be really transformative because it will really allow us for the first time to get a more detailed characterization of the clumps. So with MICADO, we will really explore this new regime that for us, for now, it's really a little bit sketchy.
As usual, I have several naive questions. But just one. I want to try to understand, because you talk about the environment. So now, isolated galaxies are mostly influenced by internal components, rather than the ones that are in the bulk of the galaxy clusters, the large scale structures. But concerning dark matter, also the dark matter halo of a galaxy may be intended as an internal effect, and we don't know how from galaxy to galaxy how the dark matter halo changes. For instance, the distributions, the density profiles, how change from one galaxy. So the question is, are there any evidence of the effect of the dark matter halo on the morphologies, and in this case, what we can learn about the dark matter?
No, I don't think, obviously, to answer this question, we need to rely on simulations because we don't have direct access to the dark matter. We know we can estimate the dark matter content, but we don't know if, for example, if there's a weird morphology. But the thing is that I would say that there could be an influence, but there must be an influence even at higher level to affect further dark matter of the galaxy, the dark matter halo of the galaxy, and then this reflects on the galaxy. What I say is that when a galaxy enters into the cluster, first the dark matter halo is disturbed. The galaxy can lose its dark matter halo because it gets merged, let's say, with the dark matter halo of the cluster itself. And then this actually affects the morphology, but I don't expect that the dark matter halo of the galaxy, in absence of external mechanisms, can affect the morphology, because the relation between, for example, stellar mass and dark matter halo are quite well known. The scatter is not too big, so I expect that the scaling relations are quite well defined already. So I don't think there is room to affect the morphology.
Related to this, I had other questions, but related to this, it doesn't mean, so there is no obvious evidence of difference of a spiral galaxy, the so-called, I think they're positive galaxies, the ones that are very much isolated, and the ones which are in clusters.
I think that the problem is where we draw the line between similarities and differences. Each galaxy is different from the other, right? So it depends if you mean a higher number of clumps or of spiral arms or bars, length of bars, but yeah, nobody has found, I think, a clear result that shows that these galaxies in super isolation have systematically larger disks or stronger bars or things like that. I think there is no clear-cut result. But the problem is it's so complicated, I think, measuring morphology. Yeah, you can go, if you start going into the details, each galaxy is different in its own category.
Okay. Curiosity, technical curiosity, PSF construction, also on morphology. So, your diagrams basically were boxed and a mass range that doesn't go below 10 to the 10.
You're talking about
the galaxies.
Sorry, I thought, okay.
The galaxy, morphology,
yes.
environment, density, relation, distance with the expected highest peaks of well, but there's a plethora of then objects that go below that. Yes. And I mean, in those cases, we don't need to go large distance because dwarf galaxies, we barely see them around here. So, and what do we know about the, how do we constrain the entity with depth of morphology? If morphology can be used for those objects as
the problem is that between galaxies in the very local nearby universe, and then what I've been showing, there is a jump in redshift that probably is not meaningful, but it's a different way of seeing things, I think, in the sense that we don't have enough statistics to start. We do not have enough, not statistics, but the different cases, massive clusters, groups, and filaments, and all the different environmental conditions for these very dwarf galaxies. So we do not have all the cases to really understand how much, or, for example, we have the dwarf galaxies in Fornax, but we have only Fornax, we have just one cluster. So it's very hard to understand if that cluster is peculiar, if Coma is peculiar. We know Coma is weird. So you cannot extend the results that we know from Coma to other clusters. But then we do not have the access yet to those galaxies. Actually, now, for example, with foremost surveys, there are some teams that are really focusing on the dwarf population, even in clusters. I don't know if you know what foremost is. It's an ESOS survey that will have different components and different surveys. And there is this chances survey that will focus on clusters, a redshift 0.04, more or less, really going down to 10 to the 8 solar masses to start seeing that regime. I think that we do not have enough statistics for now to really perform on that scale, mass scale, what we've been doing at the higher masses. It's definitely useful and interesting, and for sure, we expect that the environment, these galaxies will be even more subject to environmental effects because they have less gravitational, less capability to retain their gas. So for sure, the environment, they are the perfect candidates to characterize environmental effects.
Just last night question. How this INAF scientific community, or what the scientific came from our collaboration with MICADO, so why we need to be hands-on with the game?
Well, we need, in practical, it's important to start familiarizing with the data that with the quality of the data that we will have, trying to have this idea that the PSF will really be a key to perform the new level science with MICADO. MICADO, with no reconstruction with the PSF, I don't want to say it will be useless, but still will not be such a step change. So it's important to start thinking, familiarizing with the importance of having this knowledge. And even though INAF is a very small component in the partner, so we will not have a huge GPO nights. But being ready and knowing how to write successful proposal and why and what to request and which level of details when there will be open calls will be certainly useful and important to make the best use. And then obviously we have some treat with Morpheo, and so there are other ways. But and also I think that it would be important to start thinking also to the cases that could be developed with the SCAO, that because in the first years we will not have Morpheo. So there will be some cases that can benefit more from the SCAO rather than from the MCIO. So it's important to start thinking what to request, let's say, which proposal to write in the first years where Morpheo will not be there, because we don't know the time lag yet. So it could be an idea to start focusing on those cases that will have a higher priority.
I have a simple question. How do you think the low resolution spectral currently go in distinguish that's what this since you use this same one that has some
we haven't explored yet. I mean, I think that there will be the spectrum, but that possibility is not really the high priority right now. So we haven't started exploring yet those cases. And I think that case will be, I mean, at low redshift, there are not so many important lines in that rigidity. So it will not be super useful. But then when we get into the redshift where we can start having, for example, the fashion series or the bracket series, so it will be that we could discover some new, to develop some new calibrators for computing circummeasure rates and things like that. So even though it will be just one slit, and for the big objects, you will just get time bits.
So,
but then, but the problem is that the wavelength coverage is not optimal for the technical high redshift because it's too optimal.
So, more technical question. So, from what I understand, PSF reconstruction is going to be dramatically important for the first MICADO, and will be also as much important when there's MICADO and Morpheo together.
Yes.
Or it's less relevant and then connected with this. So we know, not all, but we used to do photography with standard techniques where you get the stars, you get the model, either from some simulation, INAF or whatever, and or from tools like now. But then in the future, I understand that this is not going to be possible with this. And how tough it is to build a PSF from this. I mean, do I get my info? This is the bulk of data I get from ISO.
This is still under construction and debate because also. Sorry.
It's not just X, but when I get my
yes,
PSF.
Yes. Even though there is a huge discussion about data transfer, data volume, the amount of data that will be stored will be huge. but yeah, the idea is that the
The end
user,
would just
yes,
have
and
a tool.
this will be the case because the PSF will vary across the field. So we don't know, we don't know a priori if you're interested in PSF here, or there. So the user will have to input the right parameters for the location in the field of view they are interested in, because it's not possible to save a PSF for each.
But that's with SCAR, not as much for.
Also for MCO.
But not too.
Not too much.
Not too much, but still.
Not too much.
Yeah.
Okay.
But still, yeah.
Okay. I mean.
It depends on how perfect you want to be and how precise you want to do your science.
The service that MICADO will be.
Yeah, it should be, hopefully it should be easy. I mean, knowing some key quantities, it should be easy to enter the information and then get your yes. Hopefully.
But that's what we had.
Okay, let's thanks again, Benedetta. For people that, se volete andiamo a cena stasera, quindi chi vuole unirsi,